Okay, so I think I'd just go with the introduction just to break off the ice. And so while we're waiting for people to come in. And today we're very happy to have a qmeets Manfred Lindner and Christian Buch. They're from the Institute, the Max Planck Institute at Heidelberg, and they will be talking about new method of neutrino detection, coherently enhanced scattering of neutrinos. So Professor Manfred Lindner is working in Max Planck Institute at Heidelberg, and his main focus is particle and astroparticle physics from both a theoretical and experimental side. One of his famous papers is minimal dynamical symmetry breaking of the standard model that is very well known. But today we will talk about neutrino detection. And then we will have Christian Buch. He's also at Max Planck Institute in Heidelberg. And he has many works on standard model concerning neutrino physics. And I think both of them will just go inside this beautiful science that is neutrino detection. So I will happily leave the chair to Manfred Lindner, and yeah, I think we can start.
Okay, thank you for the kind introduction, and thanks to everybody for your interest. Of course, I can only guess what your background is, so I will start to say from basic introduction to the field and go deeper and deeper. And I think the main point of this talk is it takes us to the smaller scales in the universe, which we also nowadays connect to the larger scale of the universe, to cosmology, but I don't have time to talk about this today. We talk about neutrinos because neutrinos are very special. They're unique messengers that allow us to look at the fundamental laws of physics in a way which is very different from others. That's why they're so interesting. Let's get going. First, the world at small scales is historically grown. We start off from people thinking particles are point particles like billiard balls, going deeper and deeper in the scales from atoms down to nuclei, to protons, neutrons, etc., down today to quarks and electrons. Historically, it was point particles. Today, elementary particles are actually the quanta of relativistic fields. It means technically quantum field theory, which is mathematically a very well-defined field. Simplified version, you can say every particle is actually like a field, like an electromagnetic field, with the wavelength being arbitrary, which is the momentum, while the amplitude gets discrete, which is the quantum nature of the particle nature. These fields obey relativistic kinematics, so particles move obeying the energy-momentum relations of relativistic kinematics. There's a lot of fields and symmetries involved. I could say more about this, that dictate the structure of the theory, and everything at the end of the day is in terms of symmetries that underlie a so-called representation. So particles are representations of the Lorentz group. They are either scalar particles, pseudoscalar particles, vector, axial vector, tensor, spinor particles. Spinor particles are spin-on-half particles are the fermions of the theory that we know. And that is internal symmetries which connect to the charges. The charges define to which interactions these particles couple. All this is encoded today in a so-called standard model particle physics, something that came along over many decades, etc. It works extremely precisely, is well justified, works very precisely, is tested different ways. Yet on the theory side, we know that it must be incomplete. And incomplete means that we have to look for the cracks and find what's missing to make it more complete. That's the overall setting. If you look at that into particle zoo, historically, you think it was everything made of up and down quarks, electrons. Then there was the discovery of generations, charm, strange, and muons. A third generation, tau bottom, top, bottom, and tau. Nobody expected that, and actually up to today, nobody understands that. These particles, so say, if you look at them, there's also the messengers, the forces, the gluons, the photons, the Z and W boson, and the Higgs boson. The matter around you is made up from up and down quarks. Protons and neutrons are made from up and down quarks. They form nuclei, they form everything, and electrons, which are the atomic shells. So you could say all these particles is irrelevant. It's up, down, and electron, which defines our ordinary life, everything that you see essentially in the telescope in the universe also. Then there's the messengers. There's the gamma, the photon, which is the electromagnetic interactions, EMB fields, that's well understood. There's sort of gluons, which mediate a strong nuclear force by being exchanged, and the W and C boson, which are connected to the weak interactions, to radioactivity, etc. And there was a big surprise that these particles select only left-handed particles. They violate parity in a way which was not expected, but that's the way nature told us. In addition, there's this Higgs boson, which was discovered something like 15 years ago, which was the missing link. So that means that made the theory complete. Now, in this picture, every particle that you see has also an antiparticle. So every electron has a positron. And so you can have duplicate these particle states here. And then the interactions are simply the exchange of these so-called gauge bosons, these mediators. For example, if you look at an electron-positron attraction, an electron coming in and a positron coming in, exchanging a photon that is scatter, or you get an electron-positron annihilation by having electron-positron coming in, exchanging intermediate state and radiating it to gammas, and so on. So all the processes can be understood as in terms of so-called Feynman diagrams, mediated by these gauge bosons, which are exchanged, and the matter particles carrying essentially these charges. That's the Lego game, so to say, and of course there's a lot of things to be said. That's of course a nice historic development, but there's something else that was a stumbling block back almost a century ago. In 1930, there was a crisis in physics, namely connected to radioactivity. First, on one side, there's alpha decays, where a heavy nucleus like uranium-238 decays and thorium-238 and an alpha particle. These guys being heavy, the uranium-238 being heavy, essentially the alpha is kicked out and takes all the energy difference between the uranium and thorium. And then what you see then is that the event rate versus the energy is a monochromatic line. All alpha particles have the same energy because this corresponds to the difference in mass of this mother and daughter nucleus. For beta decay, people expect the same. So when thorium-234 decays to palladium-234, an electron is emitted, and this electron, for the same reason, should have a monochromatic energy line. But the problem was what Hahn might have measured was a distribution, a continuous distribution. That was a heavy problem being discussed forward and backward. And in the end, it was the Swiss physicist Wolfgang Pauli who solved that in the famous strike, so to say. He said, I did something that you should never do in theoretical physics. I explained something that is not understood by means of something that cannot be observed. It means he invented the neutrino. In fact, he called it neutron then in 1930. Only later Fermi renamed it neutrino. It's changed the picture. Decay emits an electron and another particle, an antineutrino, which has no charge whatsoever. That's why Pauli was so frustrated. This particle is so weakly interacting that it will never be possible to detect it. That was his frustration coming along with this invention. The good thing was this preserves energy momentum conservation, which would have been a major strike otherwise. There's also his famous letter. He was in Zurich. He wrote actually a letter to the German Physical Society meeting saying that this was a desperate idea, etc. And so on. He doesn't dare to publish yet on it, etc. So discuss it. And he justifies his absence to say, I have something much more important to do. Then there's a ball in Zurich, and I'm not available to go to the Physical Society meeting. So he thought that going to a ball was something more important at the time than pertaining his idea about neutrinos. Later on, neutrinos were discovered, and the neutrinos had to be added then to the table of particles to matter. So there's neutrinos. And since weak interactions only couple to left-hand neutrinos, that's what you have to add. You have to add these left-handed guys. And of course, when you look at this in this picture, it almost sounds tempting to add something else here. But at the time, experiments showed nothing of that, and neutrinos were technically massless. That was the standard model for many years, up to, let's say, up to the end of most of last century, essentially. Then in exchange again, it was actually the discovery of neutrino oscillations, a quantum mechanical conversion of neutrinos of different flavors into each other, which laid the ground to the fact that neutrinos have mass. This is actually very important because it's the first solid evidence for new physics beyond the standard model. And it has, if you look in the theory side, many consequences that people discuss. In fact, if you go to the publication database and look for words like some particle, electron, whatever, etc., neutrino is the most frequent word that shows up in the titles of publications. And it's also no surprise that it was so important that it ended up to lead to a Nobel Prize of Art McDonald and Takachita in 2015. So that's an important development. And now neutrinos, massive neutrinos are standard. And now the point is, of course, since neutrinos are the door opener into new territory, new physics, the idea is, can you do more measurements standard model, whereas we know that it still cannot be complete. That said, you look at where can I do neutrino experiments, and takes us to neutrino sources. There's a list of sources that we talk about, and nowadays are reality and are measured, so say, while Pauli was desperate. The first one is the sun. The fusion process in the sun produces an enormous amount of neutrinos. If you put your thumb against the sky day and night, we go to the Earth, you have about 60 billion neutrinos in the size of your thumb every second go through. It's enormous numbers, but extremely weak interacting, so you don't notice them. Next one is the astrocosmology background. For example, supernova, old stars that become unstable and collapse because of gravity, they implode and explode, so to say, they produce enormous amount of neutrinos. In fact, the supernova in our galaxy is at this peak brightness, the brightest object in our galaxy, but it's only 1% or less than 1% of the energy emitted. If you could see neutrinos, a neutrino burst from a supernova would blind you. That's the other way to say it. Cosmology, in the Big Bang, when the universe started, neutrinos were produced as every other particle, and in every cubic centimeter of the universe, there's about 330 neutrinos flying around, here, now, everywhere. And they have a tiny mass, and add up these tiny masses, they actually add up to some non-negligible fraction of the mass of everything in the universe. Next, there's nuclear reactors. That's actually what Christian will then talk in detail. Nuclear reactors, they run from spallation of heavy elements, and they produce, of course, energy. They also produce a lot of neutrinos, antineutrinos. I will say more about this in a moment. Then there's the atmosphere. Earth is constantly bombarded from outer space by high-energy particles, protons, neutrons, gammas, etc., and they interact with the atmosphere. And in the air, they produce secondary particles, hadronic showers, produce pions, and pions decay. That produces a flux of so-called atmospheric neutrinos that rain down on us, traverse the Earth. That actually where the neutrinos were oscillations, and massive neutrinos were first discovered. Another source is accelerators. We can create neutrino beams these days by bombarding a target made of copper, beryllium, or something like that with high-energy protons, producing hadrons that decay and pions that decay. And decaying pions in forward direction produce essentially a neutrino beam in forward direction. And these beams are sent these days over hundreds of kilometers. Shown is here the beam from Chicago to Minnesota. There's another one from Geneva in Europe to Gran Sasso that is no longer existing. And a new beam is actually built from Chicago all out west of 1,000 kilometers into Minnesota and into Dakota, South Dakota. So this is a standard way to neutrinos, and they travel, even though the Earth is bound, they just travel as if nothing would be there. Another source is the Earth. The Earth has radioactive isotopes. They are there. In fact, the radioactive isotopes are historically important because they are part of the heat of the Earth. There's a heat capacity. The Earth was hot when it formed, and it is cooling. And if it only would cool without radioactivity, it would be colder today than it is. So it's a very intense geological discussion on how hot the Earth is and how much decaying isotopes contribute to that. And these decaying isotopes, they create neutrinos, so-called geoneutrinos, coming out of the Earth, etc. All these geoneutrinos inside the Earth correspond to about 60,000 nuclear power plants running constantly. And last but not least, you can make artificial sources by accumulating radioactive sources in a beta source and measure neutrinos that are emitted when this source decays. But that said, it's very interesting to look at all these sources, and people do look at all these sources today. Now, a little interlude on interactions. I gave you this table of particles, and the rule is that the neutrinos always interact in two ways, with the Z boson and W boson, so-called neutral currents and charged currents. Neutral currents are the exchange of Z boson, means it can couple to any fermion antifermion pair. So you can have a DD bar coupling to Z, and Z going back to mu bar, for example, or it's CC bar going to Z, going back to BB bar. So any fermion is antifermion coupled to Z boson and comes back to any other one. That's the so-called neutral current because it has no electric charge. A charge current couples to any pair within this doublet. So an electron and neutrino couples to double boson, or up and down to double boson, etc. So you can use this rule as a building block of so-called Feynman diagrams. For example, a neutral current diagram where a neutrino scatters by exchanging a zero boson of an electron. You can read the diagram also in the other direction by saying a neutrino antineutrino annihilate, make a Z boson, make an electron positron pair, then the charge changes. This is a charge current example where a neutrino comes in, we do this by the emission of a double boson on an electron, and the electron coming in catching double boson going to neutrino. Or here it's the neutron to proton, because the neutron and proton are made from quarks, so you can talk to the whole neutron and proton without disintegrating the bound state. That's also a charge current action. That's well understood, and these are the rules how these particles interact. The only extra rule is energy momentum conservation. Any one of these diagrams can only run if there's enough energy to make it. If you produce a heavy particle that's too heavy to be produced, then the channel is stalled. That said, you can actually discuss the sources that I mentioned. One example is, for example, is the sun. If you look at the sun, you can write down all the fusion processes of the different isotopes that exist, proton-proton fusing to deuterium, etc., and so on. Then there's all these reaction channels, and in different places in these reactions, there's neutrinos being produced. And then it leads to a solar neutrino spectrum, which is shown here as a function of neutrino energy, the so-called PP fusion cycle up here. Then there's the PEP cycle, the boron 8 cycle, the HEP cycle. This is a total spectrum of neutrinos that we should see. And actually, that's measured today. So we know this is there. It's not speculation. We see it. So by measuring solar neutrinos, you actually test all this, etc., work backwards. Reminder, the sun, as you put up your thumb, produces 60 billion neutrinos per second per square centimeter. So day and night, these neutrinos come all the way to the Earth. But if you measure solar neutrinos, you have, of course, a unique opportunity to learn something. You can use the neutrinos as messengers. An example is shown here. If you take the model of the sun here, the core where the fusion happens, which is 50 million degrees hot, while the surface is only 6,000 degrees hot, then it of course means the energy production in the fusion is inside, but it takes a diffusion process and convective rolls and all this solar physics and differential rotation to eventually transport the energy to the surface. The energy transport from the core to the surface takes 10 million years. So when you look at the sun now, for example, this picture with eruption said, this is the energy production about 10 million years ago. If you look at neutrinos, it takes only 2.3 seconds to make neutrinos to come to the surface. You look at the sun now, the core of the heart of the sun now. It means you have a very good way to look at the sun from two sides. On the surface, you learn from these observations in neutrinos, but also helioseismology, what's going on the surface. And by looking at neutrinos from the core, you look at the whole system from the other side. And by putting things together, you learn a lot about the sun, which is after all a standard star, which develops, which we can describe in sort of stellar evolution theory and so on. So it's very interesting to have this, etc. And this picture down there in the sun in neutrino is not a fake, it's a real image. You can go on and dream, that's not reality. You can think a map of the Earth in geoneutrinos. If you had a detector that detects all the geoneutrinos that are emitted, the Earth would look like this. There's the oceans, which are pretty quiet, and then there's the continents, which are more active. Find areas like Himalaya, which are more active. That means there's old rocks, which are especially enriched in heavy elements, which are still decaying. So mountains have a tendency to be more active in some sense, etc. But then you see all these spots here. And you can wonder, what are these spots here? And I'll come back in a second, right? So that's simulation. That's how the Earth would look like in neutrinos, if you have a neutrino telescope looking down on Earth. Next thing is, let's look at nuclear reactors. That's actually what these spots are. These spots are nuclear power reactors. If you look at nuclear reactor, then there's neutrino production, because you start with some heavy isotope like uranium-235. You split it up into subparts, you have fission process. In this process, there's different decay products where the heavy element that you start goes to lighter and lighter elements. And in these decay processes, there's essentially neutrinos emerge from neutrons becoming protons in these isotopes, producing electrons and antineutrinos. In Feynman diagram, which would be a downward and upward exchange double boson that break an electron and an antineutrino. So this spallation process in the nuclear reactor produces lots of neutrinos, tremendous amount of neutrinos, really. And that's why if you project out these energies are higher than the neutrinos. So look at the Earth at neutrino energy is a little bit higher than what I showed you a moment ago in that picture. you see all the places in the world where there's nuclear reactors, essentially. Neutrinos from a reactor are extremely intense and powerful. It's an extreme flux close to a power reactor, because a few percent of the energy that a reactor produces actually are released in neutrinos. If you have a 4 gigawatt thermal power, which is a big standard reactor these days, you have about 100 kilowatt in neutrinos at a distance of about 10 meters per person. It's really mind-boggling. If you go there, I have these experiments at reactors. If you go there and stand there and know that in this distance there's 100 kilowatt of energy streaming through your body, knowing that nothing will happen all the rest of your life, because neutrinos are so extremely faintly interacting that you have not to be concerned at all. They just go through. There's zillions of neutrinos going through, and all your lifetime nothing will happen. That's just these enormous weak interactions. It's really amazing. Next is, of course, this explains why neutrino experiments are huge. An example is shown here, the so-called super Kamiokande experiment in Japan. This is a detector which is about 40 meters high and same in a diameter, etc. There's 50,000 tons of ultra clean water inside there. There's 11,200 light sensors. You see this, all these photomultipliers here, 11,200. You are the pure students that clean these photomultiplier tubes. And that's really a very important thing. And they look for atmospheric neutrinos which come in from the being produced atmosphere, come in this detector, produce light signals which are recorded by these PMTs. Of course, then you have a background. Even though you have a big detector with some event rate, there's background, and then enemy is actually natural radioactivity. Natural radioactivity is, say, stuff that's around you. And that's why you need, in all these experiments, so-called background suppression. And that's why these guys go underground to avoid cosmic radiation, and they use radio pure materials to be clean enough to have a chance to see a signal that you're looking for. That means these detectors are huge, cost a lot of time and money, etc. Take this to realize. That's, of course, what it is. Backgrounds are important, just as a number to remember. A typical adult human has about 5,000 decays per second in his body. When we talk about levels which are orders of magnitude cleaner, so it's an art to build experiments, and Christian will show you, to build experiments where the natural radioactivity is down, suppressed by many orders of magnitude, to be able to extract a significant amount of neutrino events in your data. But then you have to avoid, the other thing is to avoid these huge detectors. That's the problem that we had, so say, at the beginning. We don't want to build a huge experiment that's so big, costs many, many millions, takes decades to be built. So the question is, how do you make it smaller? And there's, of course, the trick is that you can amplify the interaction rate by coherent scattering. In solid state physics, you know, let's say Bragg scattering, that there's a regular lattice of atoms, there's light coming in with a wavelength which is similar to crystal distances, and quantum mechanics tells you that you have amplitudes which add up coherently, so the amplitudes add quadratically up, and then if you have this wavelength, the distance matching, then you get interference pattern. Under certain angles, they add up coherently, produce an interference pattern with minima, maxima, etc. That's exactly what you want, etc., which is very nice. What we talk about is a little bit different. It's about, let's say, if you go to a much larger wavelength, much bigger than the distance of the crystal. So if you go to a neutrino scattering on nucleus, the situation changed that the nucleus itself is not a regular lattice. There's neutrons and protons. They don't even sit still, they move around, etc. It's just a collection of neutrons and protons, etc. So you're sending in a neutrino wave, so say, and what do they? So there's no regular lattice. You go to wavelength, which is much bigger than distance inside the nucleus. So take a long wavelength, and then there's no interference pattern. But you still add up the amplitudes quadratically. So there's still n squared coming in that enhances the cross-section, the rates for this process, because there's still this adding of the amplitude and then squaring to get the event rate. That's actually a quantum mechanical feature. So the important point is the momentum transfer in both cases enhanced by n squared, where n is the number of particles that you interact with. And of course, if you have a heavy nucleus where n is big enough, you can win because it's a big number. And that takes us to coherent neutrino scattering. That's the simple picture. It's actually the exchange of a neutrino coming in, exchanging a Z boson, this neutral particle, with a momentum that actually corresponds to long wavelength, such that it sees the whole nucleus as one object and not the quarks or the neutrons or protons separately. For that to happen, you have to look first at the coupling, and this coupling is proportional to the number of neutrons -1 minus 4 times the so-called Weinberg angle times the number of protons. And nature has that this Weinberg angle squared is roughly 1/4. So this is very close to 0. So this is essentially the number of neutrons. Means neutrinos mostly talk to the neutrons in the nucleus and are blind, to good approximation, blind to the protons. So then next thing is the momentum must be chosen at the wavelength. So you go to low enough momentum such that these waves scatter on the whole nucleus, see all the neutrons at the same time, such the amplitudes add up quadratically. That means that the energy must be below 50 MeV, mega electron volt. So this lower energy means, of course, that the cross section gets a little bit lower, and you can compensate this, have to compensate by going to very high flux. So where is the place where you have a very high flux and this low energy? And you guess the answer is you go to nuclear reactor, where both conditions are fulfilled. The cross section that describes how often this interaction happens is proportional to n squared. If you take germanium crystals like we do, then you have n around 40, then n squared is around 1,600, which means a detector that used to be 10 tons shrinks to a few kilograms. That shows the power of this coherent amplification, that it can move to much smaller experiment, not 40 meters high or something like that, much smaller and much more, much cheaper, much faster, etc. So you look at, when you start this, you look at the whole spectrum of options. You start with looking at the neutrino spectrum as we know it. This is a compilation of all the neutrino sources that we talk about, the flux weighted with the energy, because that's to say what's relevant for the scattering process. And you see what you see. This C and B, these are the neutrinos from the Big Bang, the leftover guys. These are solar neutrinos, the thermal ones, the solar nuclear reaction. These are solar neutrinos. Here are the geoneutrinos, this dashed line here, atmospheric neutrinos, and there's some other ones, etc. So this is what it is. And if you look at this, the first thing you'll see that you have to stay below this 50 MeV. So everything on the right side is out because there's no coherence. The amplification would be lost. And you see, okay, being close here, that's the best. But that's leaving out one important thing. It's leaving out other sources, man-made sources, because these are natural sources. If you go to man-made sources, you can do a nuclear power reactor. As I showed you, that you have this dark fat red line for a 4 gigawatt reactor at 70 meters. It's orders of magnitude bigger. Or you can artificially produce pions and have them decay, produce them from pion beams, this kind of enormous rate. Or you can wait for a supernova, which goes off, which also for a short moment produces a lot of neutrinos. Of course, waiting for the supernova is not what people want. So it's these red and blue options, which people realized are the way to go. And then, of course, the real detector means you have to estimate what kind of event rate you have. That means you have to multiply these detector size and the backgrounds and put everything together to make it a realistic experiment. And what we discussed here in Heidelberg is to use the nuclear power reactor, get close enough, use this enormous flux of neutrinos, use this coherent scattering, and develop a technology which was able to detect this signal and to employ technologies to make the detector as clean as possible to have the signal extracted from this background. That's what Christian will cover in a moment, but let me so say close by saying a few words about what SENS is good for. I have no time to discuss, but there's a long list of why people are interested in that. There's a very much growing interest in that. There's, of course, one is the sensitivity, so-called beyond understandable sensitivity in different ways, how this process could show new physics. There's applications like you can use this technology to monitor nuclear reactors for non-proliferation purposes. You can learn about nuclear physics in some ways. There's also the neutrino detection for pointing direction, etc. And there's also other connection to dark matter physics. There's lots of connections. It's one of the hottest fields at the moment. And pushing the experimental boundary, of course, inspires people to think of yet other things. So no surprise that there's a lot of activities in the world to try to catch coherent scattering. Here's a map that's actually not complete with all the experiments in the game. And in all this experimental game, there's now 3 observations after half a century after it was invented. One is the coherent experiment in the US, which uses stop pion beams, higher energies. Then there's the dark matter detectors, Sen, Anton, and Panda X, which see the solar neutrinos doing it. And there's Cronus at the lowest energy, the fully coherent regime. That's what Christo will cover. So nice to mention that our institute is involved in two of these. Xenon is an activity of our institute, and this is our institute. So we're very heavily involved in these kind of activities. And of course, also on the theory side. So we push this because it's very promising. That's all from my side. If you have immediate questions, we could have them now, or we could go on and Christian could continue with the second part, and then we could so say have questions altogether in the end, as you prefer.
Thank you. And yes, if anybody has any question, please go ahead. Otherwise, we'll make all at the end. Okay, perhaps people are just shy for the moment. And yeah, let's go ahead. And then I'll ask also a bunch of my questions that I had. So go.
Okay, so I hope you can see my slides.
Yes.
Okay, great. So first of all, I would also like to thank the organizers for inviting us to give this seminar today at qmeets. And in my part of the seminar, I will now focus more on the experiment that we are working on recently, which is the Conus experiment, now running under the name Conus Plus. So I will describe the experiment in a little bit more detail, and then I will also show our first neutrino observation using the seventh process at a nuclear reactor. So I will start with our collaboration. So these are the people operating and running the experiment. So we are about 20 members in our small collaboration. Most of these members are from our institute at MPIK Heidelberg, but we have also collaborators from the nuclear reactors that we use as a neutrino source. So there are two. So we started our activities in Brockdorf, which is a reactor in the north of Germany. And now we moved to Leibstadt, which is in Switzerland, and we have people actively involved in our experiment from the reactors, which is of course very helpful because it's very important to have good relation to the reactor and also good support on site if you want to do such experiments so close to the reactor core. So if you want to do such a coherent scattering experiment in general, so you need basically three ingredients. The first one is you need a strong neutrino source. So we heard that the interaction rate for the seventh process is rather high for neutrino standards, but still with a few kilogram of the detector mass, we are talking about an event rate of order of 1 event per day. So this is rather low statistics. So you still need a strong source and you have to go very close to the source to get a reasonable signal. And in our case, this is this nuclear reactor that we use. And then the second thing, since the event rate is so low, this also means that you need a very low background environment, which is rather complicated at a reactor because you have to go close to the core, which means you don't have a lot of overburden from cosmic rays, and also there's the natural radioactivity around. So there are background events from radioactivity of the surroundings that can also mimic your event signal, and this has to be reduced as much as possible. So you need some shield structure around your detectors and around your experiment to get this low background environment. And the third ingredient that you need is you need a detector which has a very low energy threshold. So in this seventh process, the small or tiny neutrino hits the nucleus, and there is of course a huge mass difference between the neutrino and the nucleus, and it's you can have maybe imagine the picture of a ping pong ball hitting a large truck or a ship, and then you have to measure this little recoil that the large object gets. And this is a very low energy event, and to detect this, you need some detectors that have this really ultra low thresholds. And in our case, we use these germanium semiconductor detectors to measure our signal. So a few words about neutrinos at reactors. So Manfred already introduced the basic principles. So you have this these fissile isotopes. You have uranium or plutonium isotopes, and they undergo fission, and then they produce fission fragments, which are enriched in neutrons, and they are not stable. So they undergo beta decay, and in each of these beta decays of the fission fragments, one antineutrino is produced. So this means on average, you have about 6 to 7 antineutrinos produced in each fission from the fragments. And then in total, this gives you this impressively high rate of neutrino flux in nuclear reactor of 10 to the 20 neutrinos that are emitted per gigawatt of reactor power in each second. So a typical reactor has about 3 or 4 gigawatt thermal power. And so with this kind of neutrino source, it was for the first time possible to measure the neutrino. And at the times of Pauli, there were no reactors, and he probably could not imagine to have such strong sources on Earth. And then in the 50s, the first observation of neutrino was then possible in the experiment of Reines and Cohen that got the Nobel Prize in 1995. And the reaction that they used to detect the neutrinos was the so-called inverse beta decay. So this is like the beta decay, but just the other way around. So it's not that a neutron decays into a proton and an electron. It's that the incoming antineutrino hits the proton and then produces a neutron and a positron. And one nice thing about this reaction is that in your detector, you typically get a coincident signal of 2 events within a few microseconds. And this gives you a nice signature that you can use to detect the neutrinos. And for this reason, this was kind of the standard technology to detect neutrinos for many years and decades. And there were a lot of discoveries made at nuclear reactors, at experiments at nuclear reactors in the context of the neutrino oscillations. We heard about this also in Manfred's talk. So this is the effect, the quantum mechanical effect that the neutrino flavors can change their state in flight. And at nuclear reactors, many of these oscillation parameters were measured. But despite this nice signature, so the disadvantage is that the event rates are very small. And now with the seventh interactions, this coherent scattering, we have basically 3 orders or 2 to 3 orders of magnitude higher event rate. And this allows that we can go from this typically ton scale detector to kilogram scale detectors with sevens. Now, if we compare the different neutrino sources that are used to detect sevens, there are reactor neutrinos, solar neutrinos, and neutrinos from accelerator. So the first observation was happening at accelerator in 2017 for the seventh effect in the coherent experiment. And one obvious difference between these sources is the neutrino flavor. So at the reactor, you have a pure electron antineutrino flux. In the sun, which is fusion and not fission, you have also a pure flux, but of electron neutrinos. And in accelerators at pion decay at rest sources, you have a mixture of different flavors. For the seventh process, it doesn't matter so much what type of flavor you have, because this process is identical, so it's flavor blind basically, and is the same for all the flavor types. But what is a difference that is relevant for the seventh measurement is the energy of the neutrinos. So at the reactors of these 3 sources that are currently used, the energies are the lowest. The solar are kind of in the middle. And then at the accelerator, this is in principle a nice source to do the experiment. However, you are at an energy range where you start to lose this coherence condition because the wavelength is getting basically too short, and you start to resolve the nuclear form of the shape of the nucleus. And so if you want to analyze your signal, you have to do corrections and take into account basically the structure of the nucleus, which is a little bit a disadvantage of these accelerators. But overall, these are complementary approaches, and all of them is useful. And then if you have all the sources and all the experiments, you can do the combination in the end and then get all the information out. So as I mentioned, we were operating our experiment at 2 reactors. We started in Brockdorf in 2018 and were running there for almost 5 years. And then we moved to Leibstadt in Switzerland. So in Brockdorf, we had our experiments at 17 meters distance from the reactor core. Now in Leibstadt, we are at 20 meters, so a little bit further away. But in both of these setups, our experiments is located really inside the reactor building, very close to the core. This environment is, of course, challenging to work there because there are several restrictions, as you can imagine. So the materials that you're allowed to bring in is restricted. Then the access is, there are very strict protocols how to enter there. There are a lot of safety rules. For example, all our setup had to be built earthquake proof and to avoid any risk for the reactor operation. Data transfer was a big issue in Brockdorf because it was not allowed to get any data out of this inner reactor building for safety reasons. So we had basically to collect our data with hard disk and bring it by car basically from Brockdorf to Heidelberg. This is now better in Leibstadt. There we managed to get this data transfer line. And then you have to make sure that environmental conditions, so all the surroundings like temperature and general situation at your site is very stable during all the measurement period, which includes periods with the reactor turned on and also periods when the reactor is off, when there is maintenance work. So also these periods are important for us because in these periods we can measure background of the experiment without neutrino flux. Okay, so this was basically about the sources. Now I come to the shield. So to protect against this environmental background and basically the radioactivity also from the reactor and all the surroundings, we have this compact shield around our detectors. So this is basically a cube of 1.2 times 1.2 times 1.2 meters. You see here on the bottom left the picture. This is the steel cage around, and this gives you the dimension of the whole setup. And then in the center you have the detectors. And this shield consists mainly of lead and polyethylene. The lead is to protect against gamma radiation from the outside, and polyethylene is good to suppress the neutrons. And the lead itself has to be also very radio pure. So typically radio pure lead is very old lead. So in this case, for example, for the inner parts of the shielding, we use lead from the Freiburg Minster, which is hundreds of years old. And this is very good in terms of this radioactive background. And also cosmic rays are very critical. So therefore we have plastic scintillators. So this is basically extra detector surrounding our central germanium detectors that measures muons that come from the cosmic rays and then veto events when there was an incoming muon. The inner chamber is flushed with radon or with breathing air bottles, which are low in radon content. Radon is a radioactive noble gas that is typically in all the environment. And since this shielding is not completely airtight, we have to remove the radon of the inner part of the chamber. And so with this setup, we are able to reduce the background of the experiment by 4 orders of magnitude with this combination of active and passive shielding. So the most critical background category in our experiment is from cosmic rays. So there are cosmic air showers. So basically, if you have an incoming particle of high energy like proton or heavy nuclei that hit the atmosphere, they can produce many particles like hadrons and pions, protons, whatever. And then these pions decay into lighter particles and leptons like muons, and also neutrons are generated. And so most of this hadronic part is basically absorbed either in the atmosphere or in the concrete of our reactor building. But for example, muons and neutrons, they can pass the concrete of the building and can create background events in our detector. And indeed, as you see in this plot on the top right, so the dominant background source in our experiment is from this cosmic radiation. So 50% basically is induced by muons and the other 50% from neutrons. And but the good thing about this background is that this is independent of the operation of the reactor. So it is basically the same if the reactor is on or off. And then you can measure this type of background during these phases when the reactor is turned off, and then you get a good model of your background. And then your neutrino signal you can basically extract by looking at the difference when the reactor is turned on, and you look at the data points there, and then you subtract your off measurement or your background model, and then from this difference you can extract your neutrino signal. So for our detectors that we use these germanium detectors of very high purity. So we have inside the germanium detector, you have this crystal of about 1 kilogram, and then you have an electrical field. Then if you have the incoming neutrino, it hits the nucleus, and this makes some ionization signals. So you produce electrons and holes, and these electron hole pairs, these are then kind of collected at your point contact, and then you get a charge signal each time neutrino hits basically your nucleus. And the amount of the charge or the charge signal is basically proportional to the energy of the ionizing particle inside. And these detectors have to be cooled, otherwise there would be too much thermal noise. So they are cooled at -200 degrees Celsius with some electrical cooling. And the good thing about these detectors is that they have these very low thresholds that are needed and a very good energy resolution. So you see here on the bottom left the cryostat. So this is basically this cooling arm, and then this copper cylinder at the left side, and inside this copper cylinder is then this germanium crystal. And this is a rather compact detector for neutrino standards. So if you have seen the pictures before of these multi-ton detectors that are normally used, and compared to this is really small. So the detectors were already used when we operated the experiment in Brockdorf, but they were undergoing some upgrades. So when we stopped in Brockdorf, on the way to Leibstadt, we had a stop with the detectors in Lingolsheim, which is a company in Alsace who produced these detectors. They did an upgrade to improve the performance of them. And then we had basically a better detectors when we started in Leibstadt. So the main improvements were we got a better energy resolution. The energy resolution is typically also coupled to the energy threshold. So if you have a good energy resolution in your detector, it also typically implies that you have a very low energy threshold. So here we made a big step forward. And also the efficiency, this is basically the probability to detect an event. So at these very small signals, there were some inefficiencies in the past, but by the improvements of the electronics and the detectors, we now are basically at 100% efficiency in our region of interest. So you can see here below 300 electron volt, where we expect our signal, there was a large inefficiency in the Brockdorf case, which is now mainly removed. So I would say the most important parameter from the detector side is really this energy threshold. So here you see some data points. If you look at the raw data of your spectrum on the left, you see in black the data points, and then you see this kind of peak at the very low energy. This is from electronic noise, and this is can be modeled with a Gaussian shape. And we set our energy threshold basically where this noise peak kind of ends. So this is at about 150 electron volt in that case. And then you see the data points start to become flat. And this flat event rate, this is basically what is our background events from the cosmic rays. And then on top of this background, we expect then our signal. So this I indicated here in green for illustration. So this is now bigger than in reality, but just to get basically the point. So we have the signal events sitting on top of the background, and then comparing our spectrum with our background model, we can then try to extract a signal. So if we look at this threshold, and now we can convert this to a neutrino energy. So, at this threshold where we currently are, we only see the high energy tail of the neutrino spectrum coming from the reactor. So on the bottom right, you see basically the red line is showing the steeply falling neutrino rate from the reactor flux. And the bulk of the neutrino events is basically below 3 MeV even, but at the moment we are only sensitive to neutrinos with energies above 5 MeV. And if we would be in the future able to even lower our threshold even more, then we would gain a lot in statistics, and then because we would be sensitive to the lower energy neutrinos and to a higher fraction of the neutrino flux of the reactor. So now coming to the results. So we had our final result in Proctor, where we did not see any neutrino signal because our energy threshold was just too high. So in Proctor, we just could put an upper limit on the neutrino event rate, but also giving this upper limit, not seeing a signal, was I think the experiment there was still a success. So first of all, we learned a lot, and second, of course, it's also important to get these limits, because there might be physics beyond the standard model. And in this beyond the standard model physics cases, for example, if the neutrino has small electromagnetic properties, then the event rate might be much higher than what you expect. And then if you have a good limit, which is rather close to the standard model expectation, then you can exclude a lot of models or theories beyond the standard model, and this helps then this theorists and to exclude basically some of these models. Then in Leibstadt, with the improved detector, we managed to see for the first time the antineutrino flux in the 7th channel at the nuclear reactor. So here on the left, basically what this shows is the data points compared to the background model. So this is basically difference data minus background model. And then you see at the low energies, there is this rising data points. And this rise and this deviation from the background model, this is basically the signal from the neutrino events which sit on top of our background. And then this bluish band that we have here with this around this black line, this is the expectation and the prediction from the standard model. And you can see here that the data points basically follow this expectation. So we are in very good agreement with the standard model. So far, there's not any hint that there is any physics beyond the standard model from that side. So the plot on the right, this shows the same thing for higher energies above the region of interest. And here you see that the data points basically fluctuate around the zero line. So this means that data is in very good agreement with the background model. And this confirms that as our background model is working and that we have basically a good understanding of our background in the experiment. So this result was published middle of last year in a Nature publication. And of course, we were very proud to get this article in this rather prestigious journal. So now putting this into the global picture, so we have now basically measurements of sevens at 3 sources. So we have the measurement of the coherent experiment at the accelerator. So the coherent experiment uses different detector classes. So we have here 3 isotopes that are used to detect the 7th signal. Then there are the solar neutrinos, which were there are first indications from the Xenon Anton experiment and the Panda X experiment. And also recently, a few weeks ago, there was a first result from LZ, which is also a similar experiment in the US. And then in CONUS, we are basically the only experiment so far who saw the 7th effect at reactors. And so given all this experiment, in the case of CONUS, we are at the lowest energies, where we are in the fully coherent regime. And we also get the highest signal rate for a single element of all these experiments. So now, before concluding, a short outlook. So what happened now in the last year? So basically, beginning of last year, we replaced 3 of our detectors by a new generation of detectors. So far, our detectors were 1 kilogram of mass, and 3 of the detectors were changed by new crystals with 2.4 kilogram of mass. So in overall, we have now more than a factor 2 more mass in the experiment, and this will increase our statistic and also our sensitivity in our run 2, which started beginning of 2025 and which is currently analyzed. So with this new data, we expect that we can improve the precision of our signal. I think we also demonstrate in this way that the technology is scalable, and we are thinking about experiment in the future at the 100 kilogram scale, but this is open, but there are first ideas for that. And with such 100 kilogram experiment, we would expect more than 100,000 neutrinos per year, which is for neutrino experiment rather high statistics already. So now beyond basic science and beyond understanding standard model and looking into beyond standard model physics, what is this all good for? So one thing that is considered and studied is if such a detector and this detection technique can be used as a tool for reactor monitoring. So the nice thing would be that this is basically a non-invasive approach that could be used for safeguard applications. And there was basically a group of people, including nuclear engineers, safeguard experts from IAEA, and also scientists looking into these questions. And some of the topics that are studied is if such a detector can be used to study reactor fuel burnup. So there is a change of isotopes in the reactor. Uranium is basically burning and going down, the uranium content, and the plutonium content is going up. And this you can basically measure. You can also test if plutonium is removed from your reactor in the context of the non-proliferation of nuclear weapons. You can do thermal power monitoring or also use such a detector in principle for nuclear waste management. Okay, this brings me to a summary. So CONUS Plus is an experiment that measured the Seven's effect for the first time at nuclear reactors using germanium detector very close to nuclear reactor cores. And with this experiment, we are able to test the standard model of particle physics, and we are also able to search for new physics. And we started about 1 year ago the second phase of the experiment at KKL Leibstadt with increased mass and better detectors. So thank you for your attention.
Thank you for the nice talk and to both of the speakers. I think we can start with some questions if there is anybody who wants to jump in. Perhaps I'll break the ice. Yeah, I have a question. Do you think you can, is there any way you can get much closer to the reactor to properly get more data or, I mean, improve
So,
your data
of course,
collection?
we want to be as close as possible, and we considered different side options. So we are already in this reactor containment, so very close. But there were indeed positions which were at a level of 13 meter roughly. So this would have been the closest. But at this position of 13 meter, it was not possible in the end because the shield would have been too heavy, and to get all the green light and agreements from all these authorities would have been too hard and too long, and therefore we decided to go a little bit further away to the 20 meter, but to a kind of safe place where we can be faster in the installation in the end. But it's very, I would say the 13 meter is almost the closest, because of course there is around the reactor core itself has already dimensions of a few meters, and then there's the reactor vessel and all this water around, and so I think you cannot be closer than 10 meters, let's say, for a nuclear power plant at least. Of course, there are the research reactors where you can go closer. There, the closest I know was 6 meters, but then the thermal power is much lower. So then you gain in distance, but you lose in thermal power in the end.
So if you take power of distance squared, the nuclear power reactor is the best place to go. And going closer, besides the technical security aspect that Christian mentioned, other points, of course, that backgrounds also change. There's more neutrons, etc. So it's an optimal distance that you can think of from the light, not below 10 meters, I would say.
Okay, I see. And then I have a general question for the both of you. Do you think, where do you think there will be the next thing that neutrinos will shed light on for new physics? Is there any guess, any safe bet that you can make, or anything?
Well, that's a more theory question, I would say, in some sense. Of course, you can speculate, and people do speculate what might be around the corner. It's also a fact that we know from all sort of experience many things. For example, if you change some neutrino properties, you easily screw up things we know from cosmology, for example. There's in cosmology, neutrinos play a very important role in structure formation, how the universe looks today. They play an important role in other things, etc., antimatter symmetry, etc. So you can just freely change things. The point was with the discovery of neutrino oscillations was a big effort to do more precise measurements of masses and mixings. There's huge experiments that we did. Where our point is, if there's new physics, it's not only mass and mixings, also the actions to change. And that's where we look. So sort of non-standard actions. At the moment, we have limits, I'll say. And as Christian showed, that the limit is consistent with the standard model. But if you think of the next run that's ongoing, if you say improve the precision error bars by a factor, be my guest, 5 or something like that. And then, of course, the question, will it be again on the standard model, will it be off? If you're off, then I promise you there will be 1,000 papers being written of trying to explain that in all sorts of ways. If on, then people will do limit setting. And as I said at the beginning, there's very strong arguments, mathematical consistency arguments, that the so-called standard model, which works so well, cannot be the final story. And the neutrinos are the first glimpse of that. So I think going off that is a good bet.
So some people think that maybe so there are from theory side some motivation, and also from experiment side are some hints that there are, for example, so-called sterile neutrinos, which could be, for example, right-handed neutrinos. And these sterile neutrinos, okay, they are not, there is no real proof yet, but this at least would be some motivated or theoretically motivated situation that many people could imagine that these exist. So sterile would mean this is an additional flavor beyond the 3 known flavors of electron, muon, and tau neutrino. So some flavor that does not participate in the weak interaction, and therefore it would be sterile. And this is typically measured indirectly via the oscillation effect.
Yeah. Another point that I consider important is the speed, right? So if you look at these huge detectors, you cannot, if you make them 10 times bigger, it's just impossible. So in other fields, in high energy physics, things get bigger and bigger, more expensive. I think our point was to develop a technology that can be scaled. So Christian mentioned this 100 kilogram. 100 kilogram means a factor 2.5 in 3 dimensions, right? Every dimension. That's it, right? And that's something that's affordable, doable within a few years, etc. And then you will talk about high statistics measurements not in decades from now, but in a few years from now, right?
That is a very promising direction. And does anybody else in the audience want to ask a question? Otherwise, I mean, you can certainly contact the the author to ask directly questions.
Sure.
Hello?
Yeah, go ahead.
Yes. So what are the features of neutrino characteristics that can be experimentally observed? Like, I think, so what the experiments are observing are energies of after the scattering of when the neutrinos scatter, and then they give out, I think, Z and W's, and so the energies are being observed. So like, so from that you are predicting different features of the neutrino. So how do you do that? Can you say that in a bit? Can you please?
So if you look at, let's say, when we compare to the standard model, we take the known particles, the neutrinos, the quarks, etc., and the known interaction, W and Z bosons, and then we can calculate with the model how many events we see. If you would see a deviation from what is expected, then it's of course up to a theorist to just come up with ideas. The ideas can be, you can change neutrino properties by giving them a sort of magnetic moment. Magnetic moment would mean that somehow there's neutrino couples to something which has itself a charge and produces a small magnetic moment. You can think of what's being called mini charges, or another way, neutrinos will have very tiny electric charges. And you can also think of new interactions, so-called NSI particles, new particles that are heavy and at the moment are not produced directly, but show up as a quantum effect indirectly in the way how neutrinos interact with matter. So people do this. So you can, for example, invent a new boson, a new heavy boson, and new fermions. And if these particles would be there, they would modify what you measure. That's if you show your limits, what you have measured, we can sort of put limits on these extra particles. masses and couplings. And there's an interesting cross connection because some of these parties that people discuss could be an explanation of the dark matter universe. Right? There's lots of interconnections as well. Right? So our thing is we essentially test how well things are described by the standard model, and if you see any deviation, then you have the spectrum of ideas how you can explain that. That would then justify another type of experiment to go after it and narrow it down. While if you have no deviation, then you don't have to build a big accelerator to test that. So I keep joking. It's a little bit like Columbus. When Columbus was going to discover some new world, he was sailing with a ship as far as possible westward, and only the second generation of ships was built to sail along coastlines. It's the same thing. We go deep now to see something, and once there were a signal deviation, then of course you would discuss how to optimally go after the effects and discriminate the different options that exist.
So concerning the energy information that you were mentioning, so of course we have some energy spectrum, and so we see basically our signal at which energy the signal shows up. But then to do the conversion from the measured recoil, because what we basically detect is the recoil energy of the nucleus. And then if you want to go back to the neutrino energy, this depends, of course, also on the scattering angle. And the scattering angle you don't know. So you can not do one by one this direct comparison. But what you can do, of course, is because we know the neutrino spectrum, so basically the energy shape of the neutrino spectrum, and then we know what to expect in terms of our measured recoil spectrum. And then you can compare that and in principle try to do this convolution in the end.
Thank you.
Good. So I think we are heading to the end. So if there is some quick question, we can go ahead. Otherwise, we thank the speakers again.
Yeah.
Okay, thank you.
Okay, thank you. Bye.
Bye.
Bye-bye.